All right, so welcome back. Next video is going to be about trying to figure out how to deal with um, number learning targets number 19, where you can write a formula for an ionic compound, as well as learning target number 20. When it comes to learning target number 20, it gets kind of weird because, again, we do have these type 1 metals and these type 2 metals, and then we also have polyatomic ions, or PAIs. Each one of these is going to have a different naming convention to it. They're going to be similar in a lot of ways, and they're also going to be similar to the covalent compound ones that we talked about with the mono, di, tri prefixes, the ones where we drop the N and we called it an ide. But there's going to be slight differences between them that are very, very subtle, and we have to be aware of them. So we'll talk about those in the future. But to this video, I only want to focus on the type 1 metals. So first of all, you might wonder to yourself something like, what is a type 1 metal? Well, a type 1 metal is a type of metal that we know the charge. So these metals have a known and well-defined charge, and they kind of come in 3 different flavors. The first one is our group 1 metals. This is also known as the first column on the periodic table. We call them alkali metals, and those are like lithium, sodium, potassium, and so forth. Francium, kind of debatable. It's a little weird. It's so unstable, it doesn't exist for very long. But still, it's in that column. We're not going to deal with it in this class. However, lithium, sodium, potassium, rubidium, cesium are all fair game. Those will all have a +1 charge to them. There's also our group 2 metals. So group 2 metals are the second column in the periodic table. They are called, if you remember, the alkaline earth metals, and that is beryllium, magnesium, calcium, strontium, barium, and radium, and those will all have a +2 charge. And there's also 4 total other transition metals, and if you remember, transition metals are the ones in the middle. We call that the D block. These are silver, Ag, which is always going to be a +1, zinc and cadmium, which are always going to be +2, and aluminum, which is always going to form a +3 ion. So these are our type 1 metals, and they are called type 1 metals, and they're grouped together because they will always have this same charge, right? You will always know this charge. So there's never any question about this charge. And so when we go back to those last 2 problems, or those 3 problems we did in the previous video, they all had magnesium in them, which is one of these type 1 metals. And so there's really not a lot of variability in how we can arrange magnesium and other elements. So there's only one way to do it, which means that when I say magnesium bromide, I mean MgBr2. There's no other way to satisfy the condition of everything has an outer octet that's full and the molecule is neutral. No other way to do it other than MgBr2, because Mg does not have a variable charge like a transition metal could, such as copper or zirconium, copper or iron or lead or something like that. So these metals are very easy to work with when it comes to naming them. It's just that metal and then the non-metal. So for our naming convention, it's pretty straightforward. So we do metal, and then we do a non-metal. We also add that "ide" to the end of it. All right, so we're not talking about polyatomic ions. That's in a different video. Because we're just doing a metal and a non-metal, it's going to be something metal and then non-metal with an ide on it. So we do like magnesium sulfide, magnesium oxide, magnesium phosphide, magnesium bromide, magnesium fluoride. These all have only one way to arrange those charges to meet all those criteria, and so there's no other name possible for it. So it's very, very easy to do. The type 1 metals are actually super, super easy to name. Now, if you look on the the activity or worksheet that you have, or you should have in front of you, there is a section that really just kind of deals specifically with these type 1 metals. They're pretty easy to deal with. If you know that one's a magnesium, one's a bromine, all you have to do is draw those Lewis structures like I showed you in the previous video, and then you can just name it pretty much the way you think you do. So let's get some examples going, and I'll try to kind of explain some of them as I go along. All right, so this is that first page that you can fill out in this packet. If I have magnesium and sulfur, I know magnesium is in that second column, so it is a type 1 metal. This whole thing, everything is going to be ionic. So we can pretty much just start off by writing ionic. So the naming rule is going to be ionic with a type 1 metal and a non-metal. Because we know sulfur is to the right of that staircase, which means that it is a non-metal. Our naming convention for a ionic and a type 1 nonmetal, we've already talked about it. It's magnesium sulfide, right? So my chemical name here is just going to be my magnesium. Why it keeps jumping around like that? That's kind of weird. So magnesium and then sulfide. And we're done. That's it. Easy. For the chemical formula, I'm going to have to figure out the charges on the magnesium and the sulfur. We already know that our magnesium, Mg, will form an ion with a 2+ charge. And at this point, I'm going to introduce a new fancy word that you can probably use to impress your friends. Fancy term. This 2+ thing, it's a charge, yes, but +2 is usually how we define a charge. 2+ is something we call an oxidization number, right? I'll write it up here. Oxidization number. An oxidization number basically means the charge. For our purposes in this class, they mean the same thing. So whenever someone says, what's the oxidization number on magnesium, you'd say it's +2. If someone says, what's the charge on magnesium, you say it's +2, right? No real difference. Sulfur, if you know, is a element with a -2. And we can figure that a bunch of different ways. We can talk about the number of jumps it makes. It can make, 6 jumps to the left, or it can make 2 jumps to the right. And it's going to do the 2 jumps to the right, which is gaining electrons. So it would become -2. Now, if I do my crisscross method, my 2 from my sulfur goes here, my 2 from my magnesium goes here, and that gives me the ratio of 2 magnesiums per 2 sulfurs. So we'll write that out first. So Mg2, 2 of them, and S2. So magnesium 2, sulfur 2. But now I look at this, I say that's not in its lowest common terms. There's a common factor here of 2 on both these. The ratio is saying 2 magnesiums to every 2 sulfurs. And if we do that ratio, we take 2 divided by 2 and we get 1. And so the real proper formula that we would use is actually just going to be S2 an S and an Mg. So 2 magnesiums to 2 sulfurs is the same thing as 1 magnesium to 1 sulfur. And so our formula is going to be just Mgs. If I were to draw the compound, I would have a magnesium, the compound, the Lewis structure for this compound. I would have an Mg right here, right? It's neutral with its 2 valence electrons. I'll have a sulfur. It will also be neutral with its 6 valence electrons, but it has a spot for 2 different electrons and a higher electronegativity than magnesium does. So sulfur is going to grab onto those electrons and pull them over to where it has empty spots. That is my representation to show the before picture. They're neutral, and they're going to go from their neutral state, which is our before, into our after, which goes over here. And after we do this bond, we're going to have a magnesium with an oxidization or charge of 2+, and we will have we use these square bracket things here. It's kind of hard to see at the bottom, that black line there, but it is a square bracket, and inside of that square bracket I'm going to put my sulfur with all 8 of its valence electrons and the oxidization number. There is 1 of these magnesiums for every 1 of these sulfurs, and I can also look at the charges, which magnesium is +2, whereas sulfur is a -2, and if I add those 2 charges together, I will get a 0 neutral. So that's one condition that's met. The other condition that we have to meet is that everything has an outer octet. By losing those 2 electrons, our magnesium has now I think that's a 2p orbital around it. Should have been a 3s orbital with its valence electrons, but when it loses them, it drops down to that 2p being the valence electron, but it will be a full valence electron, a full shell. That means our magnesium's full. Sulfur also, if you count those dots, there should be 8 of them. That's a stable octet for both of them. We've met the second condition. This is our ionic compound, MgS, or magnesium sulfide. And here over on the right side of this big long line, that is the process that we use to represent the formation of those ions and that compound. The next one that we have is copper 3 fluorine. I'm going to skip that for now. That's another video that we'll talk about. Let's get down to that aluminum. I said aluminum in one of the previous slides was a type 1 metal. So let me go back a couple pages here. Did I do that in this one or did I do it in the previous one? Here we go. All right. So this thing here, try that again. So an aluminum is in this list way at the bottom down here. So aluminum will form a +3 ion and only a +3 ion. It is a type 1 metal, and we can go and use that information to try to answer this or fill in all these boxes. So when I said that aluminum is a type 1 metal and it always has a charge of +3, I know what my symbol is for aluminum, my ion symbol with the charge. It is aluminum 3+. My oxygen, we talked about this already, it's going to form a 2- ion. And so now I have 3 positives for my aluminum, I have 2 negatives for my oxygen, and I need to crisscross them to figure out what the formula is. So my aluminum, Al, there will be 2 of them because oxygen is -2 charge. My oxygen, there will be 3 of them because my aluminum is a +3 charge. I'm taking that number 3, I'm putting it down here with oxygen, I'm taking the number 2 and putting it down with aluminum, Al2O3. And this is obviously an ionic compound, right? Because it has a aluminum, which is a metal. So we can just write our ionic. This is a type 1 metal because aluminum is a type 1 metal. And the other thing that we have are some oxygens, and we know oxygens are non-metals. So we will use this ionic type 1 metal bonded to a non-metal to name this compound, or this chemical. So if I were to do that, again, there's no prefix, so it's not dialuminum trioxide. It is going to be just aluminum oxide. Simple. Drawing that Lewis structure, I will have an Al, and since aluminum will have a 3+, that means that to get to there, it'll have to lose 3 electrons. So if it has to become a 3+ ion, that means that before it's an ion, it will have the same number of electrons as the charge it will become. So any -1, any -1 elements will have 7 around them. So it would be, I don't know how to put this exactly. If you have a negative ion, like a nonmetal, the number of valence electrons is going to be either the number of, or determined by what column it's in. But aluminum is kind of special because it's one of those transition metals, and all those transition metals around can take a special number of charges. It can take 2, or it can have 2 or 3 or 4 or 5 different charges. So aluminum is one of these really weird ones that even though it's a transition metal and every one of its neighbors does kind of whatever it wants with different number of charges, aluminum itself will not do that. It will always be a +3. But if I look at that aluminum real quick on the periodic table, let me pull that up. Where I said boron was going to be a +3 because there's a 13 above it, or because it needs to make 3 jumps to the right to get to helium. I said everything in that column will behave the same way. So boron with a +3 charge, aluminum below it will also have a +3 charge. If you have your periodic table, now would be a good time to write that aluminum is a +3 charge always. That, what was the other 2? Silver is another one. So silver will always be a +1 charge. And, was it cesium? No, cadmium, Cd. Cadmium will be a +2 charge, and zinc will also be a +2 charge. So notice how even though zinc and cadmium are transition metals, they are still type 1 metals with their known charge of +2, but they're also in the same column. So they behave very similarly when they go into bonds, when they become ions and stuff like that. So that's why our +2s are in the same column. And also notice one thing, this column has a 1 in it, right? It's 11, so 1 and then a 1. Then the second column, or the column next to it, is column 12, a 2. Interesting. And the column after that is a 3, and we have a +3 charge. So that's just one of those weird things that happens with our periodic table. When we talked back to, when we went and talked about periodic trends, we saw a lot of these things happen, and this is just another consequence of those periodic trends. So let's go back to that problem again. I have my 3 electrons around my aluminum. I have an oxygen. Let's see, an oxygen, which will have 6 electrons. And then it will have a spot for 2 electrons that will pull off of that oxygen, or sorry, off of that aluminum. Now, aluminum has an extra electron that it needs to get rid of, so we'll put a second oxygen with its 6 electrons, and then we'll draw an arrow to represent that electron going to our second oxygen. But now, even though aluminum and one of my oxygens has a full stable outer octet, I still have that second oxygen that is missing a single spot right up here. So I will need another aluminum with 1, 2, 3, 4, 5, 6. Sorry. 5 electrons around it. I think I screwed up a little bit. Let me go back just a tad. So after crisscrossing the aluminum and the oxygen's charges, we were able to get Al2O3. We know this as a type 1 metal and some nonmetals. And then this thing we called aluminum oxide, because since aluminum and oxygen have set charges that cannot change, there's only one way to arrange them and to get a neutral molecule, or sorry, a neutral compound that has everything with every element with a full outer octet. So if I want to draw the Lewis structure for this, I'll start off by drawing my aluminum. And wait, how many electrons should I draw around my aluminum? Should it be 3? Should it be 7? Should it be 2? Well, all these things want to have a stable outer octet, or 8 electrons, right? If this thing has a positive 3 charge, it means that it had a stable outer octet and lost some electrons. If that's the case, then it needs to have 3 electrons for it to lose, right? So beginning with our aluminum as neutral, it's going to have 3 electrons. There they are. My oxygen looks a lot like my sulfur. And if you look at your periodic table, you should see that your oxygen is right above sulfur. So it should have the same number of valence electrons and the same behavior when it bonds and forms a ion. So we can grab 1 electron and a second electron and put them into this space around the oxygen. Now we have a single electron left on that aluminum that we need to assign. So we need another oxygen. An oxygen with 6 electrons and 2 empty spots. That oxygen will grab one of those electrons from the aluminum, and now that still needs 1 more. And this should look familiar to you because this is very similar to what you saw in the magnesium and oxygen, right? With, the magnesium and nitrogen, where nitrogen has a -3 charge, and magnesium has +2. We're just flipping those charge numbers around. Now oxygen has -2. And so our minus thing is 2, and our positive charge is 3. But it will behave exactly the same way, and the process that we will have to deal with for our Lewis structure will be exactly the same. There are my 3 electrons around my second electron, or my second aluminum. 1 of them will go onto this oxygen, and I have 2 more that I need to get rid of off of that aluminum to make it a +3 ion. So I have my last oxygen that I'm going to draw with 2 spots for electrons. Those 2 spots will be filled by the remaining 2 electrons on the aluminum, and overall I will now have 2 aluminums with an outer octet because it lost those 3 electrons. I will have 3 oxygens with a full outer octet, and this whole thing, if I were to check it and be careful about it, my negative charges, 2 of them, -2 on each oxygen, so a total -6. We have aluminum with two aluminums, with a plus 3 charge each. So that would be a total of positive 6 charges from the aluminum, a total of negative 6 charges from the oxygen. And overall, if I add those together, that is a neutral molecule. So this is our formation process for Al2O3, which we call aluminum oxide, not that is not dialuminum trioxide. Once I've drawn out all my structures and I've pushed my arrows from my aluminums onto my oxygens, because my oxygens are more electronegative, they grab the electrons. Once I've done that, I can draw my horizontal arrow to show that in the left side, before things started, everything was a neutral thing. The aluminums were neutral atoms, the oxygens were neutral atoms, and they are going to lose or gain electrons to become ions. So I have a bunch of these things sitting around here. So what I'm going to do is I'm going to kind of condense this down just a little bit. I will do a bracket here. I will put my aluminum inside of it, and there will be 2 of them. So I put a 2 out front, right? That's like multiplying this aluminum by 2. This is how we represent multiplication, and it works a similar fashion in our nomenclature stuff for ionic compounds. In the other square brackets, I'm going to have an oxygen. Oxygen takes electrons from other things, at least from other metals, and so it will have a full outer octet in its highest level, whereas aluminum will have to drop down an energy level to become more like the noble gas that's smaller, the one above it. But that's all there is really to it. If you know the charge on this metal, and you always know the charge on a non-metal, you can put those together and you can figure out through crisscrossing that this aluminum with a plus 3 charge, there's only going to be 2 of them, and the oxygen with a minus 2 charge, we need to have 3 of those. So that is it for our type 1 metals. I encourage you to go ahead and give it a try. If you look through this, you should see some more type 1 metals. They're kind of all over the place, but there are other things going on here. For instance, this copper 3 and this magnesium 2, and I will tell you how to deal with those in the next video.